So far, in all the different proof techniques that we've looked at, we have been given a theorem, a claim, a proposition, or a conjecture, and we have been asked to prove it. In real life, this rarely ever happens. What usually happens is that you have some sort of hunch. You have a conjecture about something. So it could be, for example, like you have a hunch that this algorithm that you've written actually does prove whatever problem that you're trying to solve, or you have some sort of mathematical statement and you have a hunch that that is true. The very first thing before you try and actually go and apply one of the proof strategies to prove it is try to find a counterexample. And so that's why we're going to talk about counterexamples right here. It's not really a proof technique, it's more like a disproof technique. So what exactly is a counterexample? So a counterexample to any sort of claim, and so for example, your claim might look like for every x, p of x, a counterexample is an instance that shows that that claim is false. So for example, in this case, a counterexample would be some value of your variable, like z, such that your propositional function is false. And that would be a counterexample to this particular claim. Counterexamples are actually very analogous to whenever you're writing test cases. So you write a whole bunch of code and then you write test cases. And in those test cases, you have assertions. You have assertions that something is true or not. What you're basically doing is making up a whole bunch of possible counterexamples and checking whether or not they are actually counterexamples or not. And if it turns out that one of your assertions is false, that means you have run into a counterexample and there's something wrong with your code. So similarly, counterexamples are useful for different proof techniques or proving different theorems. So for example, let's say that you have a hunch or you have a conjecture that this following statement is true. So for example, let's say you have this conjecture. So I've conjectured that for every natural number greater than or equal to 2, if n is prime, then 2n plus 13 is not prime. So the very first thing that you should do is not try to sit down and prove this statement. You should first see if you can come up with a counterexample. Because mathematicians, computer scientists, we want to be lazy. We want to do as little work as possible. So proving something takes a lot of work, so let's see if we can disprove this by giving an example, a counterexample to this particular claim. And it actually turns out it's not too difficult to do in this case. So what do we need to do? We have to show an instance that is a natural number that shows that this claim is false. And this claim is an implication. So this is a P implies Q kind of implication. And remember, from our truth tables, the only time that an implication is false is when our hypothesis is true and our conclusion is false. So you should recall that our implication is false only when the hypothesis is true and the conclusion is false. So that means in this particular conjecture, I would have to find an n that is prime and a 2n plus 13, and I want this to be false, so I want it to be prime. So again, I want to find a number that makes this hypothesis true and that conclusion false. So let's go ahead and try letting n equal 2? Well, if we let n equals 2, then our hypothesis is true. So our hypothesis is true in this case, but what about our conclusion? Well, our conclusion, that would be 2 times 2 plus 13. So that's going to be 4 plus 13, that's going to be 17. Aha! That is a prime number. It is a prime number, so that means our conclusion, which said it's not a prime number, is false. So it's a false statement. So I have found a counterexample. When you plug in n equals 2, my hypothesis is true, my conclusion is false, therefore this whole entire implication is false. I have found an instance that shows that this claim is false. Because I showed it true implies false. So that means this is false. You should always look for a counterexample before trying to prove a theorem.